Okay, so today we are going to cover fluid kinematics. Okay, so we have completed fluid statics, and in last class we have completed buoyancy. Okay, and stability conditions for floating and uh, this submerged body. Okay, now fluid kinematics. So branch of what is fluid kinematics? The branch of fluid mechanics deals with the velocities, acceleration, and the flow pattern only. Okay, so I have already explained in statics, in fluid statics, we only focus on means the fluid element is at rest, and and we only focus on the forces which are acting on that fluid element. Okay, if this fluid element is at rest, so what all forces are there which are acting on this fluid element, that only we consider. Okay, then uh, in fluid kinematics, see, when the fluid starts moving, I've already explained it, means it will move under the influence of force. It will move under the influence of force. Now when it is moving, it will have some velocity and some acceleration, and with some pattern it will move. Okay, so in fluid kinematics we study about when the fluid is moving, we study about its with what velocity it is moving, with what acceleration it is moving, with in which pattern it is moving. That we study in fluid kinematics. And in fluid dynamics, we study about the forces due to which this fluid element is moving, and not this velocity, acceleration, and pattern. Okay, now you see, we'll go in this way. See, force, we have to study about force. So force is equals to what? Mass multiplied by acceleration. So first we'll study about acceleration. Okay, first in fluid kinematics we'll study about acceleration. Then next topic would be conservation of mass or continuity equation. So we'll study about mass and acceleration, and then we'll study about the force in fluid dynamics. Okay, so as I explained, in fluid kinematics, it is a branch of fluid mechanics which deals with the velocities, acceleration, and the flow pattern only. Forces causing velocity and acceleration are not dealt under this heading. Okay, that we'll see in fluid dynamics. Now, fluid motion. To study the fluid motion, there is two methods are there to study this fluid motion. One method is Lagrangian method. Okay, one method is Lagrangian method, and another is Eulerian method or Eulerian method, whatever you say. So in a Lagrangian method, the fluid motion is described by tracing the kinematic behavior of each and every individual particle. So they may ask in objective, in Lagrangian method, we focus on individual particle, we focus on complete control mass, we focus on control volume, or anything like that they can give in option. Okay, so this is also this point can should also be noted, because they can ask in Lagrangian method what is considered. So in Lagrangian method, you see, when fluid is flowing, let's say I have this pipeline, I have so many fluid particles here. Okay, so if I focus on only one of this fluid particle, and it is moving like this, okay, so if I focus only on this fluid particle, you see, the fluid motion is described by tracing the kinematic behavior of each and every individual particle constituting the flow. So you will have to focus on all individual particle. Okay. Now the position of each particle at any other instant of time then becomes a function of initial position and time. You see, if you want to trace, if you, let's say if you want to trace this particular particle, then let's say when it has moved to this position, it has moved to this position, you should have some reference. You should always, because when you are measuring something here, with respect to what you will measure, because here it will have some velocity or acceleration or something, with after some time it has reached here. So this much distance it has moved, this much distance it has moved. So this distance what it has moved in some time, that distance by time will give you the velocity of this thing, the particle. So when you are studying this particle here, you should know where it has started, where from it has started at time equals to 0. So at time equals to 0 it has started from here, so you should have some reference also. Okay, that's why in Lagrangian method, when you are studying behavior of each and every individual particle, then you should this position of each particle, anywhere the position of each particle is function of it becomes function of what? Initial position, from where it has started and time, and when it has started. Okay, so this is the point we should note in Lagrangian method. Clear? So that's why we can say x is function of x0, y0, z0 represents initial position, and t represents the time. Okay, so that's why this y also it will depend upon this z position. It will depend upon this initial position only. Okay, is it clear this point? Okay, so this is first thing, Lagrangian method. Now we'll move to Eulerian method. Now in this case, this method seeks the velocity and its variation with time at each and every location in flow field now. Okay, that means, let's say if you have a if you have this pipeline, and if there is so many fluid, let's say fluid is moving here. Okay, now here it will have some, let's say it will have some velocity field will be defined here. Okay, so to calculate the means if you want to calculate velocity or acceleration, then you what you will have to do is you will have to focus on single point in a flow field. Like this, I am defining let's say I'm focusing on this region, then I will focus on single point in this region, in this complete red region. I will focus on one point, and this is not a this fluid particle or anything. No, it is just a point in a space. Okay. Now next, what I will do is I will check all this. Let's say this particle, if it will move, if let's say it will move from here. So at this point, I will note what is the velocity of this particle. Now again, let's say this particle, it is moving with some interaction and all. It has moved from here. So means I will check the velocity of this particle. So whatever particle is coming, whatever fluid is coming from this side, I will check the velocity at this location. So I will check velocity at each and every location in the flow field. Okay, each and every location in the flow field, I will check the velocity. So here I am focusing on space now and not on the individual particle. So in Eulerian method, what we do, we we seek the velocity, means we will calculate the velocity and its variation with time at each and every location in flow field. So if this is my flow field, let's say I am defining this as velocity field. This is my velocity field. In this velocity field, at this point, what is the velocity? So it will depend upon so many particles which come and it will go. So this would be a little better approach, because here you will have to focus on individual space only, means a discrete different space point only, and that would be easier for you. Otherwise, if you go with Lagrangian method, you will have to calculate velocity or acceleration of each and every particle. Now you see how many particles are there in a fluid flow. So you cannot calculate the velocity of each and every particle. But here you can calculate velocity at any point. Like if fluid is flowing here, if this is my velocity field, then I can calculate velocity at any point. Any point I can calculate here, here. Let's say here we know because of no slip condition, velocity is 0. If this is pipe, at center velocity will be maximum. So in a flow field, I can calculate velocity at any location. Okay, and this would be easier for me to calculate. That's why we prefer Eulerian method for calculation, but that would be more accurate. Lagrangian would be more accurate, but again it will be a time taking calculation. This will consume less time. Okay, now, so in this case, if let's say I represent velocity v, velocity vector v. So let's say if I have a flow field, I have a flow field here. Some fluid, this is my streamline. Some flow fluid is flowing, and if I take one individual point, let's say in this point. So at this point, if I take a tangent, so let's say this represent my velocity. Velocity in this point at means at this point velocity in this direction. Okay, net velocity of at this point. Now if I want to see what is the velocity in x direction, means I want to see the component of this velocity. Now I want to see the component of velocity, same as when I have let's say if I have a box here, and let's say if I am applying a force like this in this direction, so I can resolve this force in this direction, which will be, if this is theta, then this will become f cos theta. So this is nothing but x direction force, and this will represent fy, a y direction force. Okay, two forces. So in x and y direction, I can resolve these forces. So I can individually calculate fy and fx, and then with vector addition, I can calculate f. So here also, I can resolve this velocity in x direction, which I will call as small u, and y direction, we can call it as small v, and in z direction, it is w, small w. Okay, so if you want to calculate this velocity, net velocity at this point, you can calculate, or sometimes in question they give x component of velocity is, let's say, 2, y component of velocity is 3, z component of velocity is 4. Then what is the velocity at that point? So you can do the vector addition, which is root over 2 square plus 3 square plus 4 square. So this will give you the velocity. Okay, clear this thing? It is easy only, nothing much difficult here. Okay, now next is uh, different flow patterns. Okay, different flow patterns in time and space. Different flow pattern in time and space. So you see, let's say if I take any variable, any phi is a variable. It can be velocity. Okay, it can be acceleration. So any variable which depends upon what? Space. X, Y, Z represents what? Space. And T represents what? Time. So it depends upon space and time. And any flow parameter, like velocity is a flow parameter. So any flow parameter or temperature or pressure, all these are flow parameter. So it depends upon space. X, Y, Z represents space and this represent time. That's why it is written as space and time. So to study this flow behavior, there are like four types of this thing variation. So one is steady flow. Okay. Now what is steady flow? See, if you want to uh, uh, conclude something from the flow, two ways there. Either you fix time and vary the space, or you fix a space, means fix a point in a space and vary the time and check, and then check the flow. So if I take let's say this is my pipeline, sorry, so this is my pipeline, and if I take this point, okay, and if I take, let's say, if I am focusing here, and let's say at time t1, time t1 is equals to 0, velocity here is 2 meter per second. Okay, time t1 equals to 0, velocity is 2 in, and at time t2 equals to, let's say, 2 second, after 2 second, at this point the velocity, let's say v I will take, is, let's say here it is 3 meter per second. Okay, now to understand steady flow, what we will do is I will fix a space and vary the time. Okay, I will fix the space and vary the time. So let's say I will just consider only this point. So I'm fixing space, fixing a point in a space. Now at t equals to 0, velocity 2 meter per second. At, let's say, t2 equals to 2 second, velocity is still 2 meter per second here. Then it represents what? It represents your steady flow. Okay, so flow in which fluid property at any point and any fixed point do not change with time. So you see time you are changing, but any fixed point property is not changing. So velocity, acceleration, pressure, temperature, all these properties, if they are not changing with time at particular point, then we call this as steady flow. And if it is changing, like let's say if at 2 second, at this point velocity has become 3 meter per second or 1 meter per second, either increasing or decreasing, it is changing with time, then it is unsteady, then it has become unsteady flow. So is it clear, steady and unsteady flow? So for steady and unsteady, you should check with respect to time whether time is changing or not. I mean, time you should change and space you should fix. Okay, now next is uniform and non-uniform flow. So in uniform and non-uniform flow, now we'll fix what? Time. We'll fix time and we'll vary the space point. So let's say at any time, at any instant time t equals to, let's say, 2 second, at any particular time, I will check velocity at this point and let's say this point. 2 points I will check. So here if velocity is 2 meter per second, and here also if it is 2 meter per second, then at this time velocity here and here it is same, so it is a uniform flow. Velocity is not changing with respect to space. Okay, with space velocity is not changing. But let's say if I have a nozzle like this, nozzle like this, so now if I take at any instant, at, let's say, time equals to 2 second, at this point if I check velocity, let's say if it is 2 meter per second, because area is reducing, so at the same time velocity here will be, it would be, let's say, if it become 4 meter per second. Okay, so at same time velocity here and here it is different, so it is non-uniform. So if the area, you see, if the area is changing, to maintain the mass flow rate, to satisfy the continuity equation, if area is reducing, velocity increases. And that's why if velocity at any instant at this 2 point, velocity will not remain same. So this is non-uniform flow. So is it clear? Steady flow, unsteady flow, uniform and non-uniform flow. Yes, sir. Yes, yes, yes. It can be non-uniform and steady. It can be non-uniform and steady, like in a nozzle only. This is your nozzle. At this point, if you focus at this point, the velocity will never change. It will 2 meter per second only. Now at this point it is 4 meter per second, so it is non-uniform. But at this point it will never change, and at this point also it will never change with time. Then it is steady flow but non-uniform. Any combination of that four is possible. Any combination of that four is possible. Okay, now next is material derivative or total derivative. Now what is material derivative and total derivative? So you see, it is means this derivation I will not go in detail. If you want, you can refer book, or if you have doubt, you can ask me later. So you see, material derivative is what? It is a total derivative. It tells you how any property is changing with respect to space and time both. Okay, how any property is changing with respect to space and time both. To understand this, let us take one example. You see, if I have, what is the formula for acceleration? It is change in velocity by time, delta v by delta t. Okay, now if I have a body here, okay, and if it is moving with constant velocity of 2 meter per second, okay, it is with this velocity it is moving continuously. So what is acceleration? If it is at every time it is moving with same velocity 2 meter per second, so acceleration is what? Zero. Because at time, let's say if I take at time this, at time t1 equals to 0, velocity is 2 meter per second. At time t2, let's say 2 second, velocity is still 2 meter per second. So delta v by delta t, it is 0. Now is it steady? Is it steady, this thing? It is steady. Okay, because velocity is not changing with respect to time, and acceleration is 0. Okay, now you tell me, if I take a nozzle, okay, here velocity is 2 meter per second, here velocity is 4 meter per second, and at this point velocity is 2 meter per second always, at any time velocity is 2 meter velocity at any time velocity is 2 meter per second here, and at any time velocity is 4 meter per second here. So this is steady flow. Now what is the acceleration here in this case? It is steady flow, na? Velocity is not changing with respect to time. So what is acceleration? You don't tell me the value, you just tell me whether it is 0 or not. Acceleration, whether it will be 0, it is velocity is not changing, no? At this point, 2 to 4, so you are changing with respect to space. But I am telling acceleration is what? Delta v by delta t. With time, velocity here, is it changing? No. So acceleration should be 0, na? You see, that only your answer is means you are close to your answer. You are very means you are very close to that actual answer, but you have not explained it properly. You see, acceleration. Now you see velocity here, it is 2 meter per second. But if acceleration is 0, then how come it is becoming 4 meter per second here? That you are what you have said is correct only, but you should explain like this. See, here velocity is not changing with respect to what? Time. So with respect to time, acceleration is 0. With respect to time, acceleration is 0. But you see, from here it is 2 meter per second and here it is 4 meter per second, and its velocity is increasing with space. At any instant, here it is 2 meter, here it is 4 meter per second. So with the space, the velocity is increasing. That means there it is accelerating. No, if it is not accelerating, then how come it can have 4 meter per second? How come its velocity is increasing? So actually acceleration also, so that's why in last slide, that material derivative, what I was explaining, any variable phi, it will depend upon space and time. Okay, so if I talk about acceleration, it will depend upon space and it will depend upon time, both. So we'll have to check both things, whether with time it is accelerating or not, and whether with space it is accelerating or not. Okay, so we cannot say directly that if with time, if velocity is not changing at any point, so acceleration is 0. No, with respect to time, yes, it is 0, but with respect to space, it is not 0. So still it will have some acceleration, and because of that only this thing is coming from 2 meter per second to 4 meter per second it is going. Okay, so a material or total or substantial derivative, okay, is given by two things. One is this particular term, u dou by dou x plus v dou by dou y plus w dou by dou z, which is known as convective derivative, and it is due to change in position in the field. So if you see, if I'm changing the position and if the velocity is changing, then it is accelerating. But let's say if I have a constant diameter pipe, then here it is 2 meter per second and here also it will be 2 meter per second. Because with the space here and here, if I check with variation in position, the velocity is not changing. Okay, then acceleration is 0. And with time also, if it is not changing, then that with respect to time also it is 0. Then I will tell the total acceleration is 0. Then I will tell the total acceleration is 0. But if I consider this case, and if with the time the velocity is not changing, then temporal or local derivative or rate change with respect to time at fixed point is 0. Dou by dou t, it represents what? Rate of change with respect to time at fixed position. Okay, and this represents change with respect to position at particular time. Okay, so you should check both the thing, and then only you should comment about whether the acceleration will be 0 or not. Or any property, pressure also, whether pressure is a change in pressure is whether 0 or not, change in temperature whether it is 0 or not, you should check both things. You should check with respect to time also at any fixed point, and then you should vary the space and check here and here both position, whether pressure is changing or not, temperature is changing or not, and then you should answer whether the total change of that particular thing is uh, 0 or not, varying or not. Is it clear to everyone? Okay, so I hope this thing is clear. So that's why total derivative, material or total derivative, which is represented by capital D by dt, is equals to u partial derivative of dou by dou x of any variable, let's say phi, plus v dou by dou y of this phi, plus w dou by dou z of this phi, plus again this term which is dou by dou t of this phi. Now if let's say phi is function of x, y and z, it is function of x, y, z, time is not there, then this term will be 0 only. Now let's say if it is again phi is function of time only, then this term will not be 0, but this term will be 0. But if it is a constant thing, let's say phi equals to 2, then derivative of this all will be 0. Okay, so you should check accordingly. So let's say if I give that phi is equals to 2x square y, 2x square y, then or let's say if I ask you to calculate acceleration, okay, and I am giving you velocity is equals to 2xi, okay, 2xi, okay, let and 2yj. Now you tell me what will be the acceleration? 2xi plus 2yj. So you see, first you will have to do what? You will have to compare this with ui plus vj. So u here is what? 2x, and v here is what? 2y. Now what you can do? You have to calculate acceleration. So you see, u here is 2x, v here is 2y. Okay. Now you do this. Now you can calculate this one, du by dt, which will give you what? X direction acceleration. Okay, du by dt will give you x direction of acceleration. Now that will be u is 2x. Now du by dx, okay, plus v which is 2y du by dy, plus now w is anyway 0, w is 0, plus now if I calculate du by dt, now in place of u I will directly write 2x here, I will write 2x here, and I will write 2x here. So this will become 2x and this will become 2, plus derivative of this dou 2x by dou y, derivative of this 0. Partial x is there now, and partial derivative x with respect to y 0. Then this is 0, and derivative of this 0. Time is not there, na? Time is not there. This is also 0. So it is 4x. Okay. Now this will become 4x. Now if I calculate dou v by dou t similarly, so this will become, in that case this will become 0 and this will left out. Okay, then it will become 4y. Now this has become ay, then you have to calculate a net acceleration, then this will become ax square plus ay square. Okay, so you put it here, so it will become a is root over 16 x square plus 16 y square. Okay, so accordingly your answer will come. You can take root this 16, you can take out and you will get the answer. Okay. So this is how you can calculate the acceleration part, or any variable, any variable you can, means if it is given in the problem, you can calculate. Okay. So just now I have explained this thing. Well, if this is velocity, then net velocity can be calculated with by this formula, and acceleration in x direction can be calculated like this. Okay. So this is ax is total derivative of u with respect to t, and then again u dou by dou x, it will repeat. This is the variable which we are putting here. Okay. And this one also, with this you can calculate. Similarly, you can calculate ay also. Okay. So this we this term is known as what? Convective acceleration, and this term is known as temporal acceleration. Okay. Convective acceleration, and this is temporal or local acceleration. Now, if I ask you a question, for steady flow, which acceleration will be zero, convective or temporal? If it is steady flow, convective will be zero. It is steady flow. Steady means property is not changing with respect to time. Property is not changing with respect to time. So this term will become zero. So if it is, if in problem it is given that this if it is a steady flow, then which acceleration is zero? Then it is a temporal or local acceleration is zero, because and the property steady means what? Property with respect to time. Every time the property remains same. If it is 10 degrees centigrade, it will remain 10 degrees centigrade at every time. If it is for 2 meter per second, velocity will remain 2 meter per second every time. What you are telling? Yes, space is fixed. So what? Space is fixed. So I'm not telling this is zero. Space is fixed, but with respect to time, you see, if I am telling you that this is my condition and this location 2 meter per second, anytime the velocity here is 2 meter per second, and here it is 4 meter per second. So when you are calculating this thing, then you will fix a point first. So let's say I'm fixing this point. Now I will check velocity here. It is not changing with respect to time. I'll put it 0. Now when I have to calculate this thing, then I will fix a time and vary the position. So I will take this two position. Okay, velocity is different. With respect to space, velocity is different. So this will not be 0. Clear now? Okay. Now if I tell, if it is uniform flow, it is uniform flow, then which will be 0? Uniform flow. Again, you see, again, if you see, if for uniform flow, diameter will be constant. So if I take this 2 point, velocity here 2 meter per second, velocity here 2 meter per second. Uniform means what? With respect to space, with respect to space, at any fixed time, with respect to space, the velocity will not change. So convective will become 0 in that case. Because with respect to this is telling you what? With respect to space or with respect to position, whether the thing is changing or not. And in uniform flow, the properties do not change with respect to position. In steady flow, the properties do not change with respect to time. Okay, so you see this thing is related to steady or unsteady. Okay, for steady this will become 0. For unsteady this will be it will not be a 0 thing. Okay, this particular thing, steady, unsteady. This thing, convective, this is related to uniform or non-uniform flow. For uniform, this will become 0. Convective acceleration will be 0 and this is not equals to 0. Clear? Praveen, is it clear to you? Okay. Now next is streamline. What is streamline? So for a fixed instant of time, to define a streamline, it is very important. You see, you must have studied what is streamline. If in a flow field, if you like, if this is a curve, and in a curve at any point, if you draw a tangent, and if this tangent represents velocity direction, like here also, if I am drawing a tangent and if this tangent represents your velocity direction, then this curve is your streamline. Then this line is your streamline. But there is one more thing. It should be at any instant. It's not like at this point you are drawing and then another point also you'll draw like this, and because it may change. Another time, this streamline shape itself will change. Okay, it may change. So this particular term is very important while defining a streamline. For a fixed instant of time, first you will fix the time. So at any instant you will first draw a curve like this, and then at any point you draw a tangent. If this tangent represents your this velocity, then this particular line or curve is your streamline. Okay. So this is a Eulerian method. Okay. Now, in an unsteady flow where the velocity vector changes with respect to time, the pattern of stream flow also changes from instant to instant. So that's why you should first to check whether it is streamline or not, you should first fix a time, then check, because with the time the pattern may change. So in a unsteady flow in which velocity changes with time, so pattern can change. So in this case, the velocity vector changes with time, and the pattern of streamline also changes instant to instant. Okay, so in unsteady flow the pattern can change with respect to time, but it will so to define a streamline you should first fix the time. Okay, and in case of steady flow, in a steady flow, the orientation or the pattern of streamline will be fixed. Like at any time, if the velocity remains same, like if I'm fixing this point, now at time t equals to 0, velocity is 2 meter per second. Time t equals to 2 second, velocity is 2 meter per second. Time equals to 4 second, velocity here is 2 meter per second. So velocity is not changing with respect to time. Okay, so this is steady flow, and if velocity is not changing, the pattern will remain like this only. All the this streamlines will remain like this. So pattern will not change with respect to time. So for steady flow, the streamline pattern do not change with respect to time. And if it is unsteady flow, then this pattern can change. Okay, now to calculate this streamline equation, now if you this is a curve, so every curve has a equation. So if you want to calculate the if you want to know the equation of this curve, then what you can do is, with the definition, that velocity v cross ds is equals to 0. That means if I'm drawing tangent at this point and this represent velocity, then if I take cross of the, like if this is this, and if I take small displacement ds, if this is my small displacement ds, and for this, if this represents my velocity, then cross product of this two will represent a vector which is perpendicular to this one. Okay, so velocity will not be there in that direction, means flow will not be there in perpendicular to this direction. Flow will always be along this curve, because that represents the velocity. So flow in a state, streamline represents that flow can never be along a normal to this curve. It will always be along tangent to this curve. And with this definition only, so if anything normal to this is 0, then cross product of the two vector represents 0. So this is velocity vector and this is your position vector. So cross product of these two will be 0. And if I am writing v is equals to ui plus vj plus wk, and position vector can be written as dxi plus dyj plus dzk, then if I calculate the cross product and put it equals to 0, I will get this as equation, which is known as the differential equation of streamline in Cartesian frame. So the differential equation of streamline is this. This is the differential equation of streamline in Cartesian frame. Is it clear? And velocity does not exist across streamline. So across the streamline, velocity does not. Then the definition itself will be not valid. No, definition is telling you at any point it should be along the tangent. At any point the velocity should be along the tangent. If it is along normal, then how is it streamline? Then this curve will not represent a streamline. So it is not possible that velocity, it will have a velocity in normal direction. It will always have velocity at this point in a tangential direction. And that is the this thing definition. And that's why velocity does not exist across the streamline. In this direction, it will not exist. So if it is not existing, then no fluid may enter or leave a stream tube except through the ends. So if this represents my stream line, this represents my streamline. So with this, I can, with all the combination of these streamlines, I can frame this tube. So fluid can only move in this direction. It will never move in this direction. This is what it is telling. Clear? Now next is path line, streak line. Now path line is, it is like it is the path of different fluid particle as a function of time. And two path, okay, one more thing, two streamline can never cross each other. Okay, like if this is my streamline, then this cannot represent a streamline. This cannot represent a streamline because it is crossing here. Because if it is crossing here, now it has two direction. One is this direction tangent to this, one is this direction where the fluid will move. Because at any point it can have only one velocity. Velocity means only one direction it can have. Either it can move along this direction, or it can move along this direction. It cannot move in both the direction, no? So the definition itself will not be valid. So two streamlines cannot cross each other. Cannot cross each other. Two streamlines. They will always be parallel or in some gap. Okay. Now path line. In path line, what happens? We just focus on the focus on one particle, and we just trace how it is moving with respect to time. So it is the path of different fluid particle as a function of time. How a particle is means what path a particle is flowing. Like let's say if this is fluid, if this is a pipeline, and let's say this is my particle, it will go like this. It will either takrayega, it will come like this, can go like this. So it is crossing itself. It can cross itself. Okay. So uh, two path line can intersect with one another. One more particle you take, it can cross with it. Okay. So path line can. Okay. And in path line, you are just tracing one particle. In streamline, you are fixing one space point and checking whether the what is the velocity direction at that point. Okay. Now, so you see, this is your which approach? Lagrangian approach. This is your Lagrangian approach. And I have already told you that streamline is your Eulerian approach. So this also you should note. Okay, they can ask in objective whether a streamline is a Eulerian approach or a Lagrangian approach. Path line, it is Eulerian approach or Lagrangian approach. So you should know this thing. Now, next is streak line. Next is streak line. To understand this, let's say if I have this as a injection, this is my injection. Okay, this is injection and fluid is coming like this. Now, let's say a particle A, I will call it A, B, C, D. Now, initially, this particle, or ulta I will take, this is A, B, C, D. Now, initially, this A would have been here. Initially, A would have been here. Now, it will follow this path. And let's say after some time, it has reached here. Okay, all particle has to come from here, initiate from here only, no? It will come here, then A will follow this path and it has reached here. Now after some time the B particle will come, it will reach here and then it will follow this path, and let's say it has reached here after some time, and then C will come here and it will reach here, D will come like this and it will reach here. So you see, after some time, A has reached here, B is here, C is here, D here. But they all have started from here itself. It has started from here itself. Okay. So this is, you see, from here to here, this is your path line. This is your path line for A. This is your path line for B. This is your path line for C. This is your path line for D. Now, what is a streak line? Streak line is at any instant. Again, you see, at any instant means you will fix a time. At any instant of time is the locus of temporary location of all particles that have passed through a fixed point in a flow field. Means at any instant, let's say A is here, B is here, C is here, D is here, and it has started from here. Then you join all this point at any instant. At any instant, it is here. You join all these points. Then the curve, what you are getting, this curve is your streak line. Okay. So, did you get the difference between path line and streak line? So path line refers to fixed fluid particle. Means in a path line we are just fixing a fluid particle, and means we are focusing on one fluid particle, and then we are tracing where it is going. In a streak line we refer to fixed point in a flow field. Okay, at any fixed point, this from here only it has started and it has reached a different location, you just join, and what curve you are getting, you that only is your this streak line. Okay, in case of steady flow, in case of steady flow, path line, streak line, and streamline are identical. They all will overlap. In case of steady flow, all will overlap. Okay. So you can note this point also. In case of steady flow, all the three lines will overlap. Okay. Next is 1, 2, or 3 dimension flow. So this is easy only. The number of this vector components needed to describe the velocity field is your uh, this this 1 or 2 or 3 dimension. Like if you want to define u, and if it is required only I to define the flow field, then it is 1 dimension. Now if it is required, let's say xi plus yj, then you require 2 dimension now to define x direction of velocity, then it is 2 dimension. Okay, so how many dimension are required to define a velocity flow is your velocity means how many this vector components are required to describe velocity field is will give you your dimension: 1 dimension, 2 dimension, or 3 dimension flow. Okay. Okay, this topic is not in your and this thing this HL, it will not come, I think. Translation, rate of deformation, rotation, all these things. This is in GATE syllabus. Anyway, just quickly I will tell you. Translation, rate of deformation, rotation. Okay. Translation means initially it is here, now it is moving. You see, it is simply moving in this direction. It is moving in this direction from here to here to here. Okay, it is moving in this direction. So this is translation. This is simply translation. Okay. Now translation of fluid. So if you want to calculate velocity, just you check how much it has translated in how much time. Okay. Now, so the velocity is constant in this case. Okay. Now, linear deformation. Now in linear deformation, what happens if this is my fluid element? If this is my fluid element, and because of some reason, if let's say this fluid element has elongated from this, it has elongated to this. It has elongated to this. Okay, so there is a deformation. And how is the deformation? It is a linear one. Okay, it is a linear. From here, it has moved to this much. So this much extension has happened. Okay, here this much extension has happened. So it is a linear deformation. Okay, so if it is linear deformation, and in fluid, what we call, we see again, I will relate it with strength of material. In strength of material, you might have studied, if I apply a force like this, then, and if initial length is L, and if it has deformed by small length, let's say delta L, then what is the linear strain? It is delta L by L, is it not? It is delta L by L. But in fluid, we always talk about rate. We do not talk about strain, or only means only strain. In first chapter, I have explained, already explained, that it is strain rate or deformation rate, and not only deformation. So for deformation rate, I should always divide it with time. So delta L by L. So let's say if this is my delta L in time delta t, so delta L by delta t represents what? The velocity, the change in velocity in this direction. Okay, so delta L by delta t, I will write delta U, change in velocity. So this two I will combine and write delta U with space in delta x. So it will become strain rate. So that's why this is your strain rate. Okay, so this is your linear deformation or strain rate. In fluid, it is strain rate. In your strength of material, it is delta x by L. Here, velocity by x. In y direction, it is v velocity by y. Clear? Third is angular deformation. So it can have angular deformation, like initially if it is like this. Now you see, instead of this thing, it has deformed like this. So it has moved in this direction. So there is a linear as well as angular deformation also. Angle is included here. And here also we'll define as rate of angular deformation, not only angular deformation. So in strength of material, you study about shear deformation. Okay, there it is that angle. You calculate that with respect to angle only, you define that shear deformation. Here also with respect to angle only you will define, but with rate of change of time. Okay, so this is the angle change, this is the angle change, let's say d alpha, this much angle it has included. So this is d alpha, and this one it is d beta. So this much angle it has changed by this much angle. So this much angle, but with respect to time, by dt. So d alpha by dt is what? D alpha by dt, now with some this or in first chapter only the derivation was there. So with this angle you can convert this into dv by dx. Okay, and this d beta by dt you can calculate, and you can write it as sorry, not d, dou v by dou x and dou u by dou y. So this represents your shear strain rate or rate of angular deformation. Okay, for derivation part you can refer Som Biswas book, you can refer there, you will get the derivation from here to here how it has come. Okay, or in first chapter it is simple mathematics only. You see, this is your right angle triangle. Okay, and this represents your angle d beta, and then you this is d beta, so your d beta you calculate in terms of this thing, which is this one. Okay, this divide by delta y means quickly I will just tell you, angle theta equals to this distance by this one, 10 d beta. For a small angle it will be d beta only. So d beta will be dou u by dou y multiplied by delta y. Okay, and divide by means theta equals to this arc divided by radius, or this small displacement divided by this length, which will be delta y. I mean, like tan theta you can apply. Tan theta is perpendicular by base, so this is your perpendicular, is your base, this will cancel out. So d beta will become dou u by dou y. Okay, and d beta by dt. Okay, means actually this time was also there. Sorry, this I forget to write. Del delta t was also this delta t was also there. So delta t will left out. This delta t you shift it here. So d beta by dt will become dou u by dou y. Similarly, you can calculate this with this triangle, right angle triangle. You can calculate. Okay, and you will get your this thing. But that derivation is not important here. So I'm not focusing much. In fact, this topic only I doubt they will ask any question. But in GATE we study this thing in detail. And then last one is rotation of fluid. Okay, so in rotation of fluid, similarly, rotation means, see, it is rotating. This length has rotated and reached here. This length has rotated and it has reached here. So it is rotating. So what you can do is you just calculate average of both, and that will give you the rotation by which this complete fluid element is rotating about this point. How this fluid element, how this particular fluid element about this point, how it is rotating. So you see, it is, this is rotating in this direction and this is rotating in this direction. So some difference will be there. So by some net angle only it will rotate. So we can take average of this and this. So what we can do is simply, but you see the direction is different. This is clockwise, this is anti-clockwise. So one will take with for rotation, I'm telling you, one will take with clockwise, one is anti-clockwise. So this will be d alpha by dt. Then if I'm taking this as positive, anti-clockwise, then this will become negative. So this is a minus d beta by dt. And then average of this two. So this represents your angular rotation. This represents your rotation of fluid element. So this they can ask, what is the formula for rotation? So this is your rotation formula. And if I represent means if I represent this with this thing, then my formula will become half of dou v by dou x minus dou u by dou y. And this is your rotation. Okay, fluid rotation. So this represents your fluid rotation about z axis. This is omega z. Okay, omega z means this is x axis, this is y axis, and this fluid is moving about z axis only. No, about z axis it is rotating like this. Clear? So just now we have seen omega z, it is this one. So we can have omega x and omega y, and to remember we will have this formula. Better to remember this one only. So that one is in 2D flow. In 3D flow, we'll have omega x, omega y, omega z. Okay. So omega x can be calculated with this formula. Omega y can be calculated with this. Omega z can be calculated with this. So to remember this one, what we can do, we can write it in matrix form. So half is anyway there. Okay, half is there. Then I, j, k. Okay, now dou by dou x, dou by dou y, dou by dou z. Then you write u, v, w. Now if you want to calculate, let's say omega x. So omega x, so you omega x, then this two will come into picture. Okay, because this will cancel out and this two will. So it will become half. This half is there, half. Then bracket dou w by dou y minus dou v by dou z. This is your omega x. Similarly, you can calculate omega y, omega z also. In omega y, this and this will cancel out. In case of z, this and this will cancel out, and this you can calculate. Clear? Now if all omega x equals to omega y equals to omega z, if all three is 0, then only we can call the fluid as irrotational flow. And if fluid is irrotational flow, we call it as potential flow. Okay, if fluid is irrotational flow, then only we call it as potential flow. Now what is potential flow and all that we'll see later. Okay, just you remember right now, if any fluid particle, now you see this is your fluid particle, and if it is moving about its center of mass, let's say this is my center of mass, and about this, if it is not rotating about x, y and z axis, then it is irrotational flow. But if it is rotating about its axis, about its centroid, then it is if it is having any one of it, let's say xy is 0 but about z it is rotating, yz is 0 but x it is rotating, then it is rotational flow. Okay, so is it clear how to know whether it is rotational or irrotational flow? And then comes the vorticity. Okay, and vorticity is nothing but 2 times omega. Okay, which is also, which is represent now, this we can call, write, you see in vector form we write, they can ask this also, that in vector form the rotation, the angular this angular rotation can be given by half, this represent this del cross v. Okay, so this represents your this cross v, which is represented by this thing, a cross product. Okay, cross product of v. Okay, now if I put this 2 here, then it will become 2 omega is equals to the cross this one. Okay, so this represents, see this represents your vorticity. Vorticity. Okay, so vorticity is 2 times omega. Okay, vorticity is 2 times your omega, which is, and this is known as what? Curl of v. Actually this is in mathematics, you might have studied the curl, gradient and all. So curl of v, half of curl of v is omega, and curl of v is vorticity. Okay, now these things, this detail is not required here. Actually these things we study in gate, actually in detail, all these things. Here it is not required in HL examination. There we in detail we means study about how, what is this vorticity, what is rotational flow, what is this circulation. Like we have two similar type of thing, like we have rotation, then we have vorticity, and then we have the circulation. So there is a difference between all these three. Okay, so with one figure I will just quickly tell you, okay, so that you will have basic understanding. So so first let me just tell you what is circulation. Circulation for a closed path in a irrotational field is 0, but if closed path contains singular point, okay, let me first tell you the formula itself. See, circulation is this cyclic integral of velocity in some direction. So okay, just with figure let me explain, and then I will come back to equation, otherwise it becomes little bit difficult for you to understand. So you see this figure, if you focus, if now this represents your fluid particle. fluid is moving like this. Some fluid is moving in this circular path. Okay, fluid is moving in circular path. Now this represent fluid particle. This represent your fluid particle. Now if you focus on this one of the fluid particle, let's say his nose is here and this is the center of mass. Now at about this about this point, if I compare this to whether it is rotating about this point, about this axis, so it is rotational. Now whether this thing is rotating about its own axis, so this is irrotational flow. Okay, this is your irrotational flow. So about center of mass, if a fluid particle is rotating, then it is rotational flow. Okay, about center of mass, if any fluid particle is rotating, then it is a rotational flow. If it is not rotating, it is irrotational flow. Now, what is circulation? Circulation is, if you see about, if I have four fluid particle here, if I have four fluid particle, now combined center of mass of this four fluid particle is here. Okay, if it is here. Now about this point, whether this four is moving, about this point, whether this four is moving, so it is having circulation. Now about this point, whether this four is moving, so it is not having circulation. Sorry, not circulation, vorticity, sorry. If it is moving about this four particle is moving on this point, then it is having vorticity. This is not moving, then it is not having vorticity. Okay, so vorticity is defined in some local region. Locally, whether some circulation is happening. Like if I see, like this is my sea or river. This complete is my river. And locally, if I am going through some in some boat or something, let's say I'm moving in this boat or something in this direction. Now, if I am going like this, and let's say it is having some tendency, this some fluid is moving like this. Some fluid is moving like this. Now, if it is having some tendency to move the boat like this, okay, then it is a circulation. Okay, now you see this is completely this complete thing. Okay, now this complete thing, let's say this is my boat itself, is rotating about this point here, and this is also, it is rotating about this point here. Okay, so this is your circulation. So circulation means what? If in any fluid flow, if the fluid is having tendency to rotate some particular body or something in a closed circular path, if it is having tendency to rotate my boat like this continuously, then it is having circulation. Okay, it is having circulation. But if I talk about vorticity, let's say this is my boat and four people, they itself about this point are rotating. Locally they are rotating. Okay, or nearby to you, like let's say this is your boat and nearby to here itself, you are seeing something is rotating continuously very fast. Then locally if something is rotating, okay, some chunk of fluid is rotating, that is circulation. Sorry, vorticity. Okay, that is your vorticity. And if about center of its own, if some particle or you itself is rotating about your own axis round and round, then that is your rotation. So this is a difference between these three. So you see here it is having vorticity and rotation. Here it is not having vorticity, but it is having sorry, here it is vorticity, rotation and circulation. Here it is not having rotation, not having vorticity, but it is having circulation. So some student have doubt, or they can ask a question also. If means without vorticity, can we have circulation? Yes. Here we do not have vorticity, but a case can happen like it can remain like this only throughout the flow, and it can move in this circular path continuously. So without vorticity, any body can have circulation also. A fluid flow can have circulation also. Is it clear, this thing? So the circulation is how much the tendency of this velocity vector. Let's say it is moving in this direction, no? So at this point and this point, if I draw a tangent, then what is the tendency of this velocity vector to move this complete body in this closed circular path? Okay, so velocity multiplied by in this distance, no? So for a small distance, let's say ds, how much tendency this velocity vector is having to move this in this ds distance? So v multiplied by ds will represent your what? Circulation. Okay, so here it is given the circulation formula for circulation is closed loop integral of velocity dot ds, that ds path. Okay, so this is your circulation. Okay, and uh, if I take this thing, this 2 omega was my 2 omega was my this thing, uh, vorticity, and if I multiply with this area, then it will give me what? This thing, which is your circulation. So in another word, circulation is vorticity multiplied by area, or vorticity is circulation per unit area. That's why vorticity can be seen locally. It is seen per unit area locally, but circulation is big control, means big closed loop, and vorticity is locally only. You will notice something is rotating like this, okay. So that is, now in I will not go much in detail here. So in the gate only we study this complete thing in detail, like with relation to Green's theorem. Also we relate these things. Mathematics we study, no, Green's theorem, so we relate that part. Now just now we have studied about this rotation in Cartesian coordinate, xy coordinate. In polar coordinate, that same rotation is given by these formulas: theta, r, and z direction. Okay, in this direction, means theta, r, and z direction, in polar coordinate we can calculate the rotation like this. If you want, you can take screenshot of this one, or you can write. Okay. Hmm. All these things are like in detail we study. No, these things will not be asked. I mean, rotation will, they can ask. Rotation, the rotation equation or curl, all those things they can ask. This much detail they won't ask. I'm just telling you. That's why I'm skipping so many things. Anyway, I'm skipping so many things. But few things which I thought it would be interesting to know. So I just told you. Okay, now I will come to continuity and then we'll move to questions. Okay, simple continuity. Conservation of mass is known as continuity equation. Any fluid flow, any fluid to have a possible flow, whether it is ideal, viscous, inviscid, whatever it is, whatever flow it is valid only if it is satisfying continuity equation. Okay, this is the first statement. Now continuity equation is conservation of mass equation. You have studied about conservation of mass, conservation of energy, conservation of momentum. So first we'll start with conservation of mass. Then when we'll study about force, it is conservation of momentum. Then we'll study about energy, it is conservation of energy. So three conservations we'll study. So first we are starting with conservation of mass, and conservation of mass is your continuity equation. Okay, it is your continuity equation. Now, first thing, existence of fluid flow is given by continuity equation. Existence of fluid flow, continuity equation. Now, the differential form. Now, three forms we'll study about continuity equation. This is the differential form of continuity equation. Okay, and you see again, dou by dou t is there, and then x, y, z, all three terms. So space and time, all three partial derivatives are there. Okay. So this is for unsteady flow. Okay, unsteady flow, this is the equation. Okay, in vector form we can write this same equation in vector form like this: grad dot rho v. Okay, and then dou rho by dou t. This is in vector form. So this they can ask in option, they can give which all are form of a continuity equation. So this is a form of continuity equation. In vector form, this is your continuity equation. Now if it is steady flow, if it is steady flow, then this will become 0. This will become 0, then this only will left out, or this will become 0, then this only will left out. Okay, then this is your steady flow equation. Okay, now if it is incompressible flow, if it is incompressible flow, incompressible means density is constant. It is incompressible means density is constant. If density is constant, then derivative of density with respect to anything, it is 0 only. So dou rho by dou t will become 0. Dou rho by dou t will become 0. So this will become 0, and rho will come out of this differentiation, and it will become 0 from here. It will not be present in our equation. So it will left out with this thing: dou u by dou x plus dou v by dou y plus dou w by dou z is, it represent or is a continuity equation for incompressible flow. It is for incompressible flow, but you cannot judge whether it is steady or unsteady flow. Although time term is not present here, although time term is not present here, but you cannot say it is steady or unsteady because time is not present, because density, because dou rho by dou t is 0 because of incompressible flow, and not the assumption of steady flow. This is for steady flow. Time term is not here also, it is not here also, but here we are sure that it is because of steady flow. Time term is not here, but here we are not sure because of what, this thing is not there, but we can say it is incompressible because density is not present here. So it is because of incompressible flow we are getting this equation. So this equation is valid for incompressible flow, whether it can be steady or unsteady, both. Okay, so they can means in gate 1 mark question they have asked this thing, twist they have given here. Okay, option was there, many students have gone with steady flow also. Here that twist is there, so that you should note here, that point. Okay, now there is, so this is one form. Now there is one more form of continuity equation, which is mass flow rate is given by what? Density multiplied by area multiplied by velocity. Okay, so or in from one point to another point, rho rho1 a1 v1 is equals to rho2 a2 v2. This is your mass flow rate. This is your continuity equation. Okay, this is your continuity equation. Now if for, and for incompressible flow, this is for compressible flow, if density is changing. For incompressible flow, continuity equation will be A1 V1 is equals to A2 V2. Okay, density will cancel out in that case because density is constant for incompressible flow. For compressible flow, this is the equation. So these are the forms, different forms of continuity equation. This is the most general form in differential form. This is in vector form. For steady flow, this is the equation and this is its corresponding vector form. For incompressible flow, this is the equation. And this is grad dot v, del dot v is its vector form. Okay. And this is also a continuity equation. So all these different forms are there. So they can ask in question, they can give in options A, B, C, D, which all are continuity equation, say, or which is not a continuity equation. So one will be wrong and three can be either one of this thing. Clear? Continuity equation is clear? Okay. Stream function, streak function, those things we'll see later. First we'll start solving question. From 180 to 82, you can start solving from here. Okay, so I have already told you, this thing, absolute pressure is equals to gauge pressure plus atmospheric pressure, ATM. So here it is asking gauge pressure. So it is at absolute pressure minus ATM. So absolute pressure minus atmospheric pressure. This is the answer. 183. It is conservation of mass. Just now we have seen continuity equation. 184, this I have not explained, but you might know about Venturi meter. Venturi meter. It's this I will anyway in next class I have to take this only. So this is your Venturi meter. Okay. So how to use this one? Whether we should install it in horizontal direction, we should install it in vertical direction, or in any inclined direction. How to install it? So actually we can install it in any direction. Anyway, I will explain this thing later. The question has come here, but I will explain when I will explain a Venturi meter. So this can be installed in any direction and in any location. Okay. Okay, you calculate, you just tell first 186. 186 you tell. This you can calculate later. You can note this question or take in screenshot and calculate. So hot wire anemometer used for measuring velocity, gas velocity. 187. Rotameter used for manometer. No. Manometer is used for pressure. Manometer for pressure. Hot wire anemometer or pitot tube is used for hot wire anemometer, or pitot tube is used for velocity. Venturi meter, this rotameter, all these things is used for flow, for measuring flow. Okay, rotameter is used for measuring flow. You might have done experiment in place also. Then velocity of air, all these things are different. In fact, velocity of air that will come in hot wire anemometer, not fluid. This is for pitot tube. Pitot tube, velocity of fluid. One dimension flow. See, how to understand whether it is one dimension, two dimension, or three dimension? If like v is equals to or any velocity, if I'm taking u, if it is represented by only xi, so I is required, only one direction is required to represent the velocity, then it is one dimension. If it is u is xi plus vj, and we will represent 2xi plus, so I and j are required, again j is will come. So if I and j is required, then it is three dimension. So you see, first option it is telling the direction and magnitude of velocity at all points are identical. So at every point, the direction and velocity will remain same. So only one direction is required. For all point, only one direction is required to represent the velocity. Then this should be one dimension. Second is, you see, the velocity of successive fluid particle at any point is same with time. So let's say at this point and at this point velocity is in this direction, this point velocity in this direction. So at any point, this will remain here only and this will remain here only. So it can be multi-dimension. But with time, the velocity is not changing. Okay. So this will not represent your one dimension. One dimension means it will require only one coordinate to represent the flow. Okay. So A is the answer here. 190. Straight away continuity equation. Any flow is possible only when it is following continuity equation. 191. So for steady flow, see acceleration two part, either convective or temporal. Okay. For steady flow, this will become zero. Temporal will become zero. But whether convective will become zero? Are you sure? This can be zero depending upon certain given condition. Like if it is uniform also. Steady but uniform also. Then only you can say it is zero. Okay. Then only you can say zero. So it will be zero but under some limiting condition. Okay. For steady, that wala part is zero, temporal wala part is zero, but convective, whether it is zero or not, depend upon some condition. Okay. Now 192 to we have solved, I think already solved. 192 C. Okay. 193. Velocity of successive fluid particle at any point is same at successive period of time. Yes, it is E. Again, you see uniform and non-uniform means first uniform, non-uniform related with variable position and fixed time. So time will be fixed and positions will change. So here you see at successive period of time means time is not fixed here. Time is changing. So this will tell you whether it is steady or unsteady. Okay. Now here these things are etc. change from point to point in a fluid means fluid flow means at different point the values are changing. So with different position, values are changing. That means it is non-uniform. At different position, if these values are not changing, then it is uniform. Okay, so E is the answer. During opening of wall, when you open a wall, let's say you are opening a tab, what happens? It is unstable. With time, the velocity changes and then it remains same. No, so just when you are opening, what happens? With time, properties changes. When you are just opening the wall, what happens? No, it is changing. If it is changing, it is unsteady. If it is not changing, then it is steady. So when you open a wall, what happens? Suddenly means this property is changing. No, just opening it is unsteady. Yes, after some time it will become steady. Correct. If you are not changing the some flow rate or something, all those things we are not changing, then only. Now 195. Hey, uniform is when it is steady. How it can happen? Uniform is different thing. Steady is different thing. This is related with your space. Uniform and non-uniform related with X, Y, Z, position or space. Steady, unsteady related with time. Again, you just study this thing. You just try to understand properly that uniform, non-uniform, all those things I have explained. No, again, you try to understand that one. So the answer is C. Uniform means with position, the property will not change. So if I take a constant dimension pipe, like this is a constant diameter pipe, so size is not changing. So if size is not changing, then here and here, the velocity will remain same. So this is uniform. If it is like this, let's say if it is like this, so here and here velocity will be different. Or if I take nozzle, here and here velocity, so this is changing shape. Size and shape is changing. Here also size and change is changing. This shape and this thing size. So this thing is non-uniform. This is non-uniform. This is non-uniform. But this is uniform. Okay. So size or position, you just remember size and position. These things are related with uniform, non-uniform. Time, it is related with steady and unsteady. Okay. Now gradually varied flow. See, you are correct. It is non-uniform and steady. That you are correct only. Only thing here, someone can, because here this two can have, means we can have argument on these two options. See, gradually means very slow. Very slowly you are changing. So when you see first second and another second, just nearby to like this time, and then very when time which is very near to present time, then there will not be very much change in the this thing. Means in that case there will be not very much change in the properties. But if you are telling 1 second and then another wala second, then obviously because you are varying, no, gradually you are varying. So if you are varying, let's say if you are changing the area, so more and more fluid will start coming. If more fluid will start coming, the velocity will increase. So for very small time you can say, but for 1 second and 2 second, if you are for sufficient amount of time, the property will change, no, with the time. So it will become non-steady. Okay, means unsteady. Non-steady is wrong thing. It should be unsteady. Okay, so this should be your unsteady case. Okay, this should be your unsteady case with time. But okay, for nearby time you can say it is steady. So these two are debatable in that case. Okay, but non-uniform is confirmed here. So either one we can say, it depends. So they should give this thing properly, but better to go with this only, the option. But here they should explain few more things. Just like that, so gradually it depends upon time, means how much time we are considering, how we are doing. Okay. Steady flow occurs when and one more thing, if you are like you see in but okay, means that leave it this thing, because again it depends how we are considering that question, so leave it. One type it will come steady, another will come unsteady. So okay. 197. Again Naveen is so much confused. See, steady is related to time, and uniform and non, yes, it is B, not C. It is B. Steady, no. So we should check whether with time it is changing or not. So at successive period of time, with time, which with the change in time, these properties, velocities and all these things are not changing. Okay, that means it is steady. This one, yes, it is A. Flow which neglects changes in transfer direction, means it will neglect changes in any other direction. So in one direction only the properties are changing. So one direction only is required to show the variation. So it is one dimension flow. Yes. Flow in which each fluid particle has definite path and their path do not cross each other. So which one it does not cross each other? Streamline flow. Correct. 200. This time you should be correct. This is straightforward question. $200 it is steady flow. 201. Now it is with respect to position at every point. It is same. So uniform flow. Okay, we'll try to solve these questions tomorrow. Tomorrow we'll start with, not tomorrow, I think Saturday class is there, no? Saturday we'll try to solve these remaining questions and then we'll move on to fluid dynamics. In fluid kinematics, few more topics are there. We'll try to cover, but those topics are not much, I don't think they are important. So basic things I will just tell quickly and then we'll move ahead to fluid dynamics. There we'll have so many questions. Fluid dynamics, Bernoulli's equation and all those things are there. Venturi meter, tubes, pitot tubes, all those things are there. Okay, then I will end the class. Any feedback is there? Okay, then I will end the class now, huh? Good night.